I'm Steve, and I've been working in engineering and industrial spaces for over 25 years. My team of experts covers electronics, computer science, telecommunications, system engineering, and robotics. What if we could predict failure, harness it to minimize its impact, improve the technology, processes, and training? Automotive crash tests using dummies were some of the first simulations devised to improve safety. If we look back, we see how the digital revolution changed everything. In the age of the digital twin, simulations are created in the digital world, not the physical. Now, millions of miles of driving are simulated in the production of autonomous vehicles. They are fully immersive sensory learning environments, from machine learning to video games, to smartphones, smart homes, smart cities. Today, real-time 3D and simulation tools allow us to restrict failure to virtual testing environments and keep it out of the real-world vehicles, facilities, and job sites. I'm going to explain how my team used Unity to create a hitchless towing system to make it safer and easier to move heavy equipment. This robot is an excavator that has autonomy and collision avoidance. The first thing we need to do is build a virtual environment where our robot can run around and learn how to operate. In this case, the environment is a digital twin. What is a digital twin? The digital twin is the core environment by which we're able to program and train a robot to execute a behavior. We give the digital twin as much data as we can about locale, and now it's operational and behaving according to the laws of physics. You can design, build, test, deploy, and operate very complex systems in interactive and immersive ways in our digital twin. It's as perfect a facsimile of the real world as we can make. By connecting the digital twin with real-world data, it becomes an incredibly powerful tool. It will be very easy to pinpoint and track objects, but we need to collect real-world information first and correlate it. We start by creating a digital representation of our environment. We can create a digital twin in a number of ways. We can create a digital model where a designer hand draws every element. We can scan the environment using technology like photogrammetry, using a drone-mounted camera. Or we can use LiDAR, which produces an incredibly accurate representation of the environment, and depending on the type of LiDAR, can keep our digital twin up to date in real time, constantly scanning for changes in the environment. For our twin, we want to include elements like weather and lighting, because those are real-world environmental conditions that the robot will be exposed to. The creation of the virtual sensor that is the analog of the physical sensor is incredibly important. It's one thing that Unity does very well with its simulation technology. Through that innovation, we are able then to allow a robot to see a virtual world in exactly the same way as it would see a physical world. Now that we've built a digital twin of our environment, we can place our robot in that environment and start to program it to operate in the manner that we want. We have to build a navigation system for this robot to traverse this digital environment. So we show it a trail to follow. We want our heavy equipment to follow the path of a lead vehicle driven by a person. Therefore, we'll use a high-precision GPS attached to the vehicle to generate a breadcrumb path for our equipment to follow. We can generate the path using any one of several methods, like a digital twin in conjunction with real-time 3D technology, or a human operator can manually generate the path for a robot to follow. Now our robot knows where it is in our digital representation of the world and where it's supposed to go. Now it has to get there safely and avoid running into obstacles and structures. It has to see the world it's operating in and learn to avoid obstacles and adapt its path. For this task, we use machine learning, where the robot learns the right behaviors through trial and error, operating in our digital twin, just like we learned from crash test dummies of old, but virtually and much faster. The robot now sees the digital world through a virtual sensor that behaves just like the real one. It will fail a lot, millions and millions of times. But with each failure, it learns what works and what doesn't. Over many attempts, it ultimately learns how to complete the task we've set out for it. So we've given it a digital twin of its location. That is the knowledge of the physical world. Sensors to experience the real world, and machine learning algorithms to process all that information. Now we have a smart robot that just happens to be an excavator. So what's next? You can use digital twins with both static and dynamic data to optimize operations across countless applications. Such as improve transport logistics, increase safety, reduce environmental impacts, conduct inspections and field maintenance on energy sites, improve airport security and resource planning. We're now on the threshold of the fourth industrial revolution, a digital transformation of the way we work, the way we live, how we manufacture goods and build our cities, how we harness energy and maintain our infrastructures. The best way to predict the future is to design it.